Good evening, hello everybody. We are about to start our next Advanced Programming Specialist Group meeting, which is joined with a Fortran group. For this particular training, we selected a topic on programming of Coarrays for parallel processing in Fortran 2008 and 2015, which we were presented by Dr. Anton Shterenlikht from Bristol University. And we're here to see some understand animations which demonstrate how the things work. Tom?
Thank you very much. Thank you for inviting me. I'm glad to know that somebody is interested in modern Fortran. You asked me before to say a few words about who still uses dead and outdated language, and of course you would be glad to know that everything we rely on our daily life is still built on Fortran. Air traffic control, nuclear power stations, rail networks, defense, industry, finite element calculations, CFD maybe moved away to C++ mostly, but a lot of solid mechanics is still done with Fortran. Weather simulation, climate modeling, the biggest Cray users still use Fortran. For a good reason, that when results matter and when performance matter, that's the best language. There's nothing better. The only thing that's better is the modern Fortran, which is so great that I hope that by the end of the talk you'll all run away and start using Fortran. Because not only it is a next evolution of Fortran. Fortran, of course, underwent quite a few changes throughout its history. From 77 to 90, big battles were fought there. Then Fortran 2003 with the first introduction of object-oriented features and IEEE floating point calculations, and now 2008, which has been published in 2011, with mostly Coarrays, although quite a few other changes were done. And now 2015 is hopefully going to be published next summer. I just participated in a meeting in the US of the Fortran Standardization Committee where we looked through country comments, and there will be a collection of those, and this will be soon passed back to ISO for basically bureaucracy. Lots more parallel and Coarray features there, which I'll briefly talk about here. And some of those, by the way, are already implemented and ready to use right now. So my plan is, I have 45 minutes, right? Okay. My plan is to talk for half an hour about Coarrays, what they are and how to use them. Maybe for 10 minutes about some specific examples from our research work on fracture simulations. And then at the very end I want to say a few words about the computational physics group, which is the hat I'm wearing today as well. I wear several hats today. About what we do and how this connects, hopefully, with some areas of interest for the audience. So what I'm showing here is the course that I teach on demand to Bristol HPC users. I'll actually be teaching this again next week. Of course, I'm not going to go through all the details. It's designed for the whole afternoon, just a few basic features. And if you have any questions, please shout straight away. So what you see here is a valid Fortran 2003 program. Some features maybe not all of you are familiar with. You can now have allocatable character, which was a big problem before. You don't need to know in advance what the length is, so it's the length being decided on assignment, and derived types, and the source allocation, and a few other interesting things. But you compile it, in this case with the Intel Fortran compiler, and you get some answer. Now this, with very, very modest modifications shown here in red, is now valid Fortran 2008, a Coarray program. So this is now a parallel program. And one of the goals of the Fortran committee was to make as little syntactic change with maximum impact. So variables with square brackets, all of those, are now called Coarray variables. And what happens is, at runtime, multiple copies of the executable are running asynchronously. So standard SPMD model. In Fortran speak, these are called images. And there are various ways to affect the number of those images, just like with MPI ranks at runtime and compile time. In this case, what is shown here is environment variable. I want to run on 7 and I get 7 outputs. So if you're familiar with MPI, and most of you of course are, then it's very similar so far. Obviously, depending on the compiler, the options will change. So what I will probably talk today is mostly the beginning images, execution control, execution segments. I want to mention also do concurrent, which is new in Fortran 2008, which is specific type of the loop that tells the compiler that all iterations of the loop are independent, so the compiler can optimize. And then a little bit briefly about the 2015 features and a few consequences of this Coarray design. So, images, again, is the Fortran speak for the executing executable. But the standards say nothing about what it is. It could be thread, could be an MPI process, could be anything else. So really what you have now is the design which is one layer above the particular parallel implementation. As far as I know, it's the first ever attempt to create a design like that. And indeed, with Cray, they use their proprietary DMAPP libraries. Intel implements Coarray via MPI. OpenCoarrays project uses MPI and GASNet. And various other possibilities are possible. The syntax going together with Coarray is very similar to array syntax. There's a lot of co prefixes. So for an array variable, it would have been subscripts, lower bounds, upper bounds. For the Coarray part, we're talking about co-bounds and co-subscripts, upper and lower bounds. Now the last upper co-bound is never specified. It's asterisk because you don't want to hard-code in the program how many images there are. It is always left until the runtime. And what you see here is actually a slightly more complicated concept where there's multi-dimensional layouts of images over the available resources. This is all, of course, only matters for the algorithm designer, for the programmer. So I can think of my executing elements arranged in a linear array or a 2D or a 3D array, which is what we do in our fracture work. It makes more sense because we're dealing with three-dimensional models, and we split those imaginary three-dimensional chunks and delegate those chunks to processors. Some basic rules, but I guess it's not really that interesting to you probably. Just to mention that it makes no sense to declare Coarray parameters because all Coarrays do, the declaration of Coarrays, it means that you make a memory space on a processor, on a thread or whatever, on a processing element, accessible to others, and therefore if it's a parameter and multiple copies of the executable are created, there's no need to exchange it. So the parameter could be always private. There are lots of new intrinsics. This image tells you the number of the image, something like MPI rank. Image index is the inverse, so if you give the input as an image index, you get as the output as a co-subscript set. And num images gives the programmer the opportunity to find out the number of images. So there's a program here that exploits all those with 3 Coarray objects. There's a linear, scalar Coarray, a scalar Coarray with 2 codimensions, and again scalar Coarray with 3 codimensions. And it's interesting to know that one of the consequences of this very simple design is that there will be sets of indices for some number of images which will have no corresponding image attached to them, which graphically can be illustrated like that. If I'm running this program on 10 images, then because of the declaration, here I logically arrange my processors in a two-dimensional array. -2, -1, 0, 1, 2, and the second index will go 1 to whatever it takes to fill my 10 images that I'm executing on. Here it's just linear from 1 to 10, and here 2 in the first dimension, 1, 2, and this will be 1 to 5. So there's a nice arrangement schematically shown here. Each cell here is an element of the array. But if I run the same program on 17 images, I have to choose the upper last codimension such that there is enough space for all images, but there will be some combinations of indices which do not have a corresponding image. So there's slight potential for programming error, but then probably nobody will want to use 17 images anyway. So this is an example of how we use it. What you see here, the colors represent the image number. Consider this some solid mechanics model. I'll tell you later what it is. Three-dimensional model, and the chunks of it are distributed to separate images. And in this case there's 64, in this case 18, and these are the matching declarations, three-dimensional grids. So in this case the last upper codimension will be 3, in this case the last upper codimension will be 4, only at runtime. Okay? Now one conceptual difference between MPI and Coarrays is that in MPI typically we talk about model partitioning. So we envisage a large model and then we split it into chunks and delegate chunks to processors. In Fortran it's the opposite idea. You declare local arrays on an image, and then by considering that a collection of local arrays together make a large model, you construct a large complete model from smaller chunks on individual images. Now remote calls are at the heart of Coarray design, and this goes to the brilliance of the original ideas due to John Reed and Bob Newbridge in all the way back to 1990s, I think. Nowadays we call this single-sided call, and therefore you can say that Fortran is a PGAS type of language. So remember that this code will be executed by every single image unless I put some control, execution control, if then or something. So every thread of execution, whatever it is, again could be a processor or thread, doesn't matter, we'll get to this point and execute this instruction. What it says is that the value of this variable I on image 5 will be taken from the value of this variable on the current image. If a Coarray variable is used without call subscripts, then the reference is always to the local copy. Okay? So this obviously, as written, will be a race condition. Every image will try to write into the memory of image 5, which is not a good idea. But in principle, this is a remote write. This is a remote read, so again every image will get to this place and will assign the whole array on my image from the same array on image with subscript set 33. And no participation on the remote side is needed, which is a brilliant idea, provided that the software is implemented correctly. And this, of course, is usually done through symmetric memory idea, which causes some restrictions on the way arrays are allocated, memory is allocated. Okay? Here, local copy only. There are no co-subscript sets or co-subscript notation, so I refers to a local variable, J refers to a local variable, and here I'm just copying from J to I, but I is a Coarray variable. I can then broadcast to do whatever I want. Okay, so to avoid races and deadlocks, we need some execution control. Sync call is very simply a global barrier. Very useful, very simple idea. And together with the barriers comes the idea of execution segments. This is a Fortran terminology. Every image control statement separates the program into two more execution segments. In this case, there's only one sync call, so there will be a first execution segment before and the second execution segment after. And the rules are quite verbose, but basically all statements that happen before sync call on any image precede all statements that happen after sync call or any other image. So this ensures data integrity. That's a quote from the standard. Sync image is slightly more flexible because it's not a global barrier, it's a multiple to multiple sort of barrier. So this is how I might use it. If this image equals 3, on image 3 I want to synchronize with images 2, 4 and 5. And there must be corresponding or matching sync image statements on those 3. So I would have these 3 statements. If this image is 2, sync with 3. If it's 4, sync with 3. And if it's 5, sync with 3. Asterisk is allowed, and meaning that this image must synchronize with all others, and this is usually a broadcast pattern. If my image is 1, synchronize with all others. If it's not equal to 1, synchronize with 1. So every image will wait for the first one to usually set its data. But after that, images from 2 to n do not have to wait for each other. They proceed asynchronously. And of course, we know for performance at scale, you want to exploit asynchronous execution as far as possible, overlapping computation and communication, all that. So, again, remember that this is the same program, identical program, one program, but multiple copies of the executables. This statement will be executed on image 3, and all those will be skipped, and on image 2 of those 4 statements only this will be executed, and so on. So I get a pairwise synchronization. Again, there's a long-winded text in the standard, but essentially, if there are 2 sync images somewhere, everything that precedes the matching sync images on image P will happen before everything that happens after sync images on image Q. Or whatever they say, T and M here. Typical example, swapping the value between 2 images. I have to use here 2 pairs of sync images. Make sure that the data is ready for copying, and after I copied it, make sure that the original variable is free to be overwritten again. But typically that's the communication pattern. Could be done in a different way. Of course, you got quite a lot of flexibility. Yeah, this just shows what happens on different images. So this is the program. This is the exact program. And this is what every image will see. This is what image 1 will see. Image last one. And all the other images will essentially do nothing because they're neither first nor the last. They'll skip all those statements. So the output will be, where is it? Yeah, 1 and 5 swap places. 3, 2 and 4 are unchanged. Okay, do concurrent. I mention it here because, for 2 reasons. It's new to Fortran 28, but also I want to compare this with OpenMP. Qualitative and not exhaustive comparison. So there's a long list of restrictions what cannot appear inside do concurrent, for the obvious reason that all iterations must be completely independent. So you declare, you guarantee to the compiler that yes, all my iterations are independent, do whatever you want with them. In 2015 there are quite a few extra details on do concurrent, really making it very similar to OpenMP. Shared and private variables and quite a few different other clauses. So for example, this line would be completely fine inside the concurrent, every iteration is independent. Here the order is important, so this would be invalid. In my very subjective opinion, restrictions severely limit its usefulness. But there are obviously some algorithms where this is completely fine, and then you're up to the you're starting to talk about performance. And I believe the performance will definitely improve. It's still a new feature, and that most people are reluctant. They prefer to use OpenMP directly. So a simple illustration of the symmetric memory. I mentioned some of these ideas already, and implementation details. Very simple example, embarrassingly or nearly embarrassingly parallel program. There's only single collective call at the end, but calculation of pi using Leibniz-Gregory series. Typical performance on up to 4 nodes on the Bristol cluster. So we get nice speed up, reduction in time on a single processor, 16 cores. As soon as we cross the barrier, we lose in performance. This was done with Intel 16, and Intel has improved a lot since those days. And they admit that when this was happening, they didn't really care about performance, they just wanted to make a standard conforming. But for comparisons, here are 2 key fragments with Coarrays, MPI, OpenMP, and do concurrent. And you can see for yourself how much similarity there is. So there is a loop in a loop for chunks of the sequence done on every image or on every rank here. At this stage, technically, before 2015 is published, Coarray collectives are not really standard yet, so we had to use here manually written collective, but with MPI you got a collective provided by the specification. Do concurrent, it's done with 2 nested loops, but essentially the inner loop is identical, and this is a simple OpenMP program. So for this very simple parallelization strategy, very simple problem, embarrassingly parallel or nearly embarrassingly parallel, really all 4 are usable. And this again is my subjective, very subjective comparison on various categories. So these are Coarrays, do concurrent, OpenMP, MPI, whether they are standardized, Fortran standard, shared memory, distributed memory, ease of use, flexibility, performance. Coarrays are this line, and in my opinion, Coarrays can give you very high flexibility and performance, comparable to that with MPI. But in my opinion, again, they're much easier to use than MPI, because it's a higher level of abstraction. And the single-sided nature of the calls make it very, very intuitively obvious how to structure your remote calls. However, it comes at a price. I think I'll just mention, I wouldn't go into the details, just mention on a few other things you can do with Coarrays. Allocatable Coarrays are completely fine, very similar to standard allocatable variables. Again, on allocation, the last upper co-bound is never specified, so this is left to the runtime. But they must be allocated with the same bounds and co-bounds on all images. This goes to the idea of symmetric memory. So these allocations would not be valid because here the size of the array is different, here the co-size is different, co-rank is different. Which means that symmetric memory will not work. There will be different, not aligned objects in memory. Otherwise, allocatable Coarrays are great. And another thing coming from the design, again from the symmetric memory idea, is that there is implicit synchronization when allocation happens. If array is allocated on one image, it must be allocated on all images, because this is when your symmetric memory is decided. So allocation could be costly. You probably don't want to allocate too often. Now, if it is an impediment in your program that you really don't want to have allocated to the same size on all images, you can go around this through derived types with allocatable components. So in this example, I have derived type with a single allocatable array, and then I create just a scalar of this derived type, right? But each scalar has a component which is an allocatable array. Now that allocatable array could be allocated to any size, because that is not a coarray. Okay? So value, percent sign means component. I allocate the size equals to the image number. On image 1 will be size 1, image 2 size 2, image 3 size 3, and so on. That is completely fine. Really, it becomes almost a pointer. You can point to anything you want. So I run it, and on image 1, this is my array, just a single element. Image 2, my array is 2 elements long. On image 3, 3 elements long. This works very well. Termination. Now, as soon as your program becomes parallel, there are complications to do with the idea of a termination. So, in a serial Fortran program, there's no question about it. It runs successfully until it gets to the end or stop statement. But in a parallel program, you want to envisage a situation of some exceptional condition, abnormal condition. You might want to do something about it. And there is a new intrinsic introduced error stop. The stop is now reserved for, you might call it normal termination. In fact, it is called normal termination in the standard. And error stop is abnormal termination. Error stop basically says the runtime environment abort as soon as possible. No point proceeding further. Normal stop is when one image maybe has completed execution, it reached the stop statement, or it might have reached the end of program while the other images are running, but it does not affect the other images. Its data is still available for other images to use. So here, what do I do here? Avoid dividing by 0. Okay, if image 1, I just issue normal stop statement. My image 1 stops at this point. It does not execute this instruction, but it does not affect the execution on the other images. If I change this to error stop, of course, depending on the relative timings, in this case, what I have is I get no output at all, and as a side product, you can see that actually I get MPI abort, which tells me that Intel implementation is using MPI. Use it for truly catastrophic conditions. Okay, very briefly about 2015 features. So, although collectives have been available on Cray probably for 10 years at least, they haven't been standardized. They will be standardized in 2015. Just a month ago, we're still finalizing those details. And OpenCoarrays also support collectives as well. This is a simple example. CoSum, number of images and assigned to image 1. Image number is assigned to image 1. I get 15. Some atomics, those two have been available in 2008 already. In 2015, a lot more atomics are added, and really atomics, probably atomic use is the way forward. Now, one problem I glossed over is that as soon as you move from two-point communication to a single-sided communication, your synchronization approach is changing dramatically. If I want to write to the memory of the other image or read from it without its participation, I need to do something to let the other image know when something is happening, when some requirements for synchronization. With two-point communication, there's no problem. Send, receive, both synchronize, proceed further. Whereas here, it's not so simple. So, atomics, like one shown here, and sync memory, which provides segment boundary. So basically, the compilers are not allowed to move statements across sync boundary. Work very well together. And really, I think when 2015 will be implemented in multiple compilers, will be a significant improvement in performance. This will definitely outperform sync images and of course sync all being a global barrier. There is always obviously a critical section, very similar to to MPI, so only a single image can proceed at one time, at a time. There are locks. I haven't used them very much in my programs. And the biggest 2015 feature will be teams. So you can delegate certain tasks to particular teams of images. You can talk about functional parallel programming. The example that John Reed always quotes is from weather simulation, where they can do different processing for land, sea, and air. You can create teams. You can, with form team, you can change inside the team. When you end team, you get back to the original team. You can also use these capabilities for fault tolerance. You can allocate certain images, number of images, which are doing nothing at the beginning. When there are software, hardware failures detected, you can bring those into existence and move your computation across. Very ambitious, very powerful feature, but we'll see how it works. Events have been around for ages in other languages. Now this is part of Fortran. You can post an event, wait for an event, and query. So for instance, I don't have it here, I have it in another example. If I have a Halo exchange in three-dimensional case, I do not need to know who posted. All I want to count is that I have to receive 26 posts. In three-dimensional grid, if I count diagonals, I have 26 neighbors. As soon as I receive 26 posts, that's it, I can proceed. I got my Halo information. These are status values: failed image, stopped image. No, this is function, yes. Image status, stopped images and failed images can provide the program with a lot of information about the status of the runtime environment. Okay, just to say that there already appeared quite a few books, straightforward undergraduate level books with Fortran, with Coarrays examples. I think this is roughly in order of fraction of the book dedicated to Coarrays. MFE is the most detailed, Walter Brainerd's, and so on, and so on. Okay, a few words on what we do with Coarrays in Bristol. This is taken from a recent talk at the Parang conference in Hungary. I'm in a solid mechanics group. We deal with fracture a lot, and particular problem with fracture in heterogeneous materials where continuum fracture mechanics doesn't work very well. So here you see popular examples: carbon fiber, reinforced polymer, reinforced concrete, bones, polycrystalline materials, metal matrix composite, nuclear graphite. So what do? We treat microstructure as a cellular automata device. It's a structured grid, and we also couple it with finite elements. Finite elements is unstructured grid, so it provides so-called cafe multiscale model, where finite elements supply stress, strain rate, maybe temperature fields, and the evolution is done on the CA level. Here you see grain boundaries, cracks propagating cross grain boundaries, and cracks and individual grains merging to form macro cracks. Now, a few related problems we have. There is no native Fortran parallel I/O. There was a long fight, a long discussion at the Fortran committee. In the end, no consensus could be reached. Some people say it's just not possible to write a cohesive specification because it's so OS and hardware dependent. So what do? We use MPI and we get quite, on the previous generation of national system, which was Hector 2.3 gigabyte, but for some reason we're struggling to get above 1 gigabyte per second with NetCDF and HDF5, although we know that MPI can reach 14 on Archer. The models could be quite big, up to terabyte in some cases. So this is the example of a microstructure with 1 million grains, and each grain is 100,000 cells. For pure computation with no I/O, we can get a nice speed up, about 1,000 up to 32,000 cores, or maybe beyond that. And this is with collective co-sum. Other techniques are not doing as well.
So you have one image per core?
Yes, one image per core, yes. One image per core. So for finite elements we use Paraffin, which is a scalable, really very portable general purpose finite element library. Used a lot in nuclear. This is nuclear fusion from Column Center for Nuclear Fusion. Some work done with biologists, dinosaur tracks, trying to reconstruct the biology, anatomy of the dinosaurs from the observable tracks left. And this is microstructure faithful modeling where CT scans or rather X-ray tomography, XRD scans are reconstructed into a microstructure, is then meshed, and the continuum simulation is done. It could scale for some problems at least up to 60,000 cores. Now this is the key for our multi-scale design. The material CA, which is done with Coarrays, is a regular grid. A phi mesh body is always, or at least there's a possibility, always irregular. And they really, the key feature is they take the same space. It's the same, they occupy the same space. At least parts of the microstructure might be sticking out of the phi, part of the phi are sticking out of the microstructure, but those are of no interest to us. Schematically, if I assume that I have 4 MPI processors and 4 images, then I might have a situation like this. So this chunk of the MPI somewhere here will have to communicate with Coarray stored on image 2, because this part of the microstructure, which occupies part of the same physical space, actually lives on image 2. Okay? Because I have no control over which image is 1 and which image is 2. This is completely out of my control. This is down to the runtime, the same as MPI runs, of course. So it so happens that the MPI, the finite element mesh allocated on processor 1, will not talk at all, will not communicate at all with microstructure stored in the same processing element. Just one example. So this is 3-dimensional model, a bar and uniaxial tension. The mesh here is semi-transparent for clarity, but you can see a block of microstructure. And part of this microstructure is inside of the finite element mesh, and that part shown here, just the grain boundary is revealed, just that part will participate in two-way information exchange. Stress and strains send one way, serial automata iterations are done, and the new microstructure state is obtained, and then damage variable is passed back. So this is cracks on 1110 and 110 planes on individual grains merging into macroscopic crack, which is generally speaking normal to the maximum principal stress direction, which is what we want. On the phi scale, if you just look at displacement field, your crack is visualized through mesh distortion. Now we had a successful Archer embedded science and engineering project, in which case we managed to replace all-to-all communication with nearest neighbor, and we increased the scaling limit from about 2,000 to 7,000 cores. So this is for cafe model, combined serial automata finite element. Right, just show you a few animations. Where are we? Here. just for illustrative purposes, so this is typical shoebox brick volume of microstructure. It makes it very, very easy to program the fact that this is always a regular grid. Yes, some of the information is not really useful at all if my finite element mesh is curved, but it's so much cheaper to do a simple logic and not to worry about wasted cycles, because cycles are cheap. Now this is a very interesting modeling result, because this is not something we can easily obtain from experiments. It would take a lot of slicing and dicing and polishing and etching to get this information on 3D scale. So these are grain boundaries visualized only. It's a useful result. And two fracture results, so it's an iterative process, of course, and every iteration there's cracks can grow for on one cell size, and this is probably 300 or 400 iterations, and there's obviously corresponding time attached to that. And you can see that even though it seems like a chaotic structure, what is emerging at the end is that there is definitely a global macro crack emerging out of this chaos. There are some artifacts here which we're working on, but there is a macro crack plane. What did I want to say? Oh yes, it was here, I think. We also work together with Tau Tools and Analysis Utilities team, which is a profiling tool, very, very portable profiling tool, and they managed to implement Coarray support. But all that we discovered was that Intel implementation is rubbish. Everything is dominated here by MPI win and lock. MPI receive is there, and my program is taking very, very small fraction of time. And here somewhere, where was it? It was even worse. I think that's the worst, yeah. That's the worst. For a simple case, for the pi calculation, it's not too bad. The first row here is my program, pi Coarray, and win and lock is here. So they implemented this through using MPI RMA calls, but they didn't do it very. I think they didn't optimize it very well. So I think results with Intel 18 will be a lot better than these results. And very recently we had a short access to tier 0, Heiselhelm system in Germany, which is one of 6 top EU systems. And we managed to achieve scaling here to maybe 300 nodes, beyond which the Cray runtime collapsed, and it took them a month to realize that it's not fixable and they're going to wait for a new release. So this just tells us that really even Cray support for Coarrays is still not very mature. And of course it's always a cycle. As there is no mature implementation, users are unlikely to use. As there are no users, the implementation is not mature. So I encourage all of you to give it a go on whatever platform you have and report back good and bad experiences. Now I was very interested to observe this. So on XC40, which is I think one of the latest generations of Cray systems, you can get energy reported as well as all the other metrics. And interestingly, so from going to 10 to 100 nodes for a larger model, we reduce the energy. So not only it's running faster, but also it takes less energy, which is really a very exciting result, as energy is likely to dominate discussion on HPC for considerable time in the future. Energy is really becoming the key concern. Okay, so that's it about the Coarrays. Just 2 minutes on the computational physics group. So recently I was elected the chair of the CPG, and I wanted to say a few words about what we do. It's one of the largest groups of the Institute of Physics. According to the numbers they give us, it has over 11,000 members, and we're very keen to engage with anybody. and everybody. It was groups like you or anybody else really. So what we do, of course, is like any group of a charitable body, we plan activities and we distribute reasonably small amount of money for the benefit of the aims, to achieve the aims of the Institute of Physics in our case. So we do organize joint events, we co-sponsor meetings and conferences. For example, IRP, Computational Physics Group, co-sponsors the annual Fortran group meeting just here in this building. We do a, I think I had it here actually. There is a PhD thesis prize which we award annually, and there's a newsletter, and we will welcome new members like you perhaps. Thank you very much.
Question time.
So I just ask about this membership. Is it open to members, not people who are not members of the Institute of Physics?
No. The idea is to attract members to the Institute of Physics.
Just like we attract members to the PGAS.
No, it isn't. A lot of groups are open in the PCS.
Well, I'm sure you can be, just like with BCS, you can be on the mailing list if you're not a member. But there's a list of probably shortened list of topics of interest. I'm sure we do a lot more than that with 1,100 members. Pretty much any area of computational physics.
What is the distribution of your membership geographically?
I started on the 2nd of November this year, so I'm not sure. There's an action on one of the committee members to get this information. But I'm not sure we'll be able to. Apparently, I've been very careful about data protection, so also we have to see what we can obtain from them. I'm not sure. If you're interested,
Just curious.
I'll let you know when I find out myself. I don't know.
I have a question on Coarrays
Yeah.
rather than physics. How do you go about debugging Coarray program?
Right, yeah. So this is just a slide. This is Cray, which is a profiling tool on Cray. Not debugging, profiling. But occasionally you can find that something is going fishy just from profiling data. With debugging, as far as I know, only Alinea Forge has Coarray support. But I think they have restrictions on the compilers they support with that. So I haven't checked for a while. Last time it was on Intel, but not on Cray, and these things keep changing, probably with some business pressure and customers. Yes, so tool support is one of the weaker areas, and again, it's this cycle of lack of user demand, lack of vendor investment. As far as I know, there are no other debugging tools. Profiling, if you use the Intel or OpenCoarrays implementation, meaning if it's implemented over MPI, you can use quite a few open source tools. The Scholastica, Scorpy, Cube, all will support it because it just goes underneath to the MPI calls. But debugging, yeah, is a problem.
Is there a big open source community associated with Fortran?
Well, hard to say. Hard to say. My network died. I'll show you if I can. OpenCoarrays is a BSD licensed project. So if you're using GCC, I think 6, yeah, I think starting from 6, it would understand the syntax, but there was no underlying transport library. So OpenCoarrays is the BSD licensed project that implements the library. And you see here you can have a very easy installation on those platforms. Apart from that, I don't know, if you follow Complan, Fortran, Usenet group, there's quite a lot of people keen to inform others about their successes. So, as far as I know, it's only OpenCoarrays, open source. Intel are interested, but I think they have been under a lot of pressure to implement the object-oriented features for the last 2-3 years, so they didn't really spend that much time. IBM have no implementation, at least nothing open to public, because again, they tell me the business pressure is more on the business customers, business revenue. So,
What about NVIDIA?
right,
Is
so
there anything where you
there was no NVIDIA representative on the Fortran committee for a number of years, but now there is one, and he says they're very keen. They're very keen to provide an implementation. They're definitely working on it. There is nothing yet, but they're working on it. I think again it's probably to do with their accelerator focus, and now they realize maybe it's not that sustainable anymore. They have to diversify, so yeah, it's coming. And then of course there is another thing, maybe you're aware, maybe you know, there is another open source Fortran compiler called Flan, which is based on PGI front end and LLVM backend. It's BSD licensed, not GPL. So the hope is that it will be picked up by a lot more customers and users for whom a GPL license is not acceptable. It doesn't support Coarrays yet, but it's being very actively developed.
One more question. In parallel processing, there is all known problem of deadlocks.
Yes.
How it is handled in this parallel programming?
The standard text is crafted very, very carefully to avoid deadlocks in standard conforming programs. So if you follow the rules, you should not have a deadlock. I think, I was arguing with my colleagues on the committee about that, I think it's not possible to have a standard conforming program which will deadlock. But if you write very complicated code, of course, it's very hard to check whether it is standard conforming or not. So this idea of execution segments is crucial, and understanding, really internalization of this idea is crucial for the programmer to write correct code. Whereas, as far as I understand, with things like MPI, it's your programmer's responsibility to ensure there are no deadlocks. Here, you're not really thinking about deadlocks, you're thinking about the rules. It says in very clear language, this is prohibited, that is not allowed, and so on and so on. As long as you do not break those rules, you should be happy.
So, sorry, I can't relate, but I mean, regarding those rules, I mean, is it possible to have some, whatever hint-like tool to check for these, or is it something that ultimately does remain with the programmer to make certain the rules are adhered to?
Well, the rules are in the standard. Standard is an open access, available to all to read.
Yes, but I mean, is there a way to check, given the program, does it conform to the standards? A bit like, well,
Is there any tools?
Some checks can be done at compile time,
yeah.
but by no means all. If you really write complicated code, particularly if you implement your own routines, calling other routines for inter-image communication, it cannot be done at the compile time.
Yeah. Well, I mean,
At runtime, no. Maybe Alinea will pick some of those, but I haven't really tried that.
I mean, at one time it's in many cases too late. I was more thinking of that. Well, I mean, for some languages you're getting tools like lint, or if you like another example, well, XML or HTML validators will go, I mean, with a very fine coon through.
Right, but things which
are sometimes things that are, well, maybe more like bad smells rather than guaranteed violations.
Yes.
They look like they could be.
Yes, so it's no different to any other compiler check-in or warning message. Sometimes you get compilers being overcautious, and you get warnings about variables potentially not being initialized, where you know that they are definitely being initialized. Somehow compiler logic made it think that it wasn't. So things which are static, yes. But things which are dynamic, which are not known at compile time, very hard to diagnose. Not compiler has got a reputation for being very, very good at that, but NAG is not good for performance, and they haven't got Coarray implementation yet.
To a certain extent, vTune basically provides a bit of a support to try and get the traces for you, but there's no way that you could really verify a particular program is free from deadlocks and all sorts of stuff.
Yeah, well, I mean, that's why I was asking, I mean, well, is it more like smells or something of that sort rather than like a hard proof that, well, this can't be right. Anyway, yeah, I mean, it's not really right for me.
I doubt there will be any tool that can say with some certainty on a real production program whether it will deadlock or not, because a lot of the details will just not be known at compiler.
This reminds me of one case that many years ago one guy was developing debugger for parallel programs, and he noticed the effect that there was certain program when it runs on its own, there was a deadlock. When debugger was attached to trace it, there was no deadlock. Because
Yes.
debugger was introducing some latency, so the timing changes slightly, and there is no deadlock.
Yes. Happens a lot, of course. Or you run it on, you've done your testing, you couldn't find anything, you gave it to somebody else, they cannot make it work. In the end, it turns out they run it on a number of images you never tried, and on that particular number of images, some logic is broken, and you get a deadlock or race or something else.
Okay, no more questions?
Yes, just to think about this performance side a bit more. I mean, really, what you're doing is for performance. Otherwise, you just use one processor, and your grandson will look at the result and so on. But so you're doing it for performance. So are people starting to understand the measures of performance? You know, what you expect from a given implementation. People start out saying, yes, I can see I need about so much, and this machine should provide it, or it doesn't provide it. For example, you know, just to understand how often you synchronize, is it too much for a given implementation and so on?
I guess this is the same question could be asked of any other programming language. With MPI, you have the same issue. I think there is only very little you can do in advance, all the theoretical performance calculations based on your assessment of the hotspot or bottleneck, basically, where most of your time is spent. A lot will become apparent only after you do some initial profiling where time is actually spent and what's the extent of your parallelization. But I would add that there's yet second reason for parallelization, which is nothing to do with performance, is the whole capability idea. Some programs just don't fit in the memory otherwise. For example, for some of the fracture simulations, we're not particularly worried about performance, but about the size of the model. The model is so big, we really need to have statistics for the microstructure of that size. And the model becomes very big, so we have to parallelize just to get it to run.
Okay.
So you reported certain energy measurements. I'm curious, how did you measure them?
Oh, these are just what is reported by the Cray
Cray 14 nodes.
AP run or whatever environment. The batch queue basically reports this.
So you didn't really do any.
No. I haven't noticed this on any other system before. I think that probably pressure from the data centers and from HPC directors on Cray and others, I guess,
So
made
it's
them
not
introduce this
really,
measure.
so it's not really not necessarily true reflection of your program. It could be all sorts of things happening on those nodes, right?
Could be, yeah, could be. Although the upward trend here tells me that even though I haven't exhausted the speed up capabilities, if I want to keep the energy under control, then I already lost. So basically, the point of this slide is that if you ignore this bit, which is positive news, the rest is very bad news. The game, which was for the last 20 years, the game in HPC was faster, faster, and faster. We start to realize actually it's not the only game. We have to worry about the energy, and that is because nobody cared.
I think what I really kind of observed out is basically when you increase the number of nodes, energy is going to go up for sure. But what was curious was that between 10 and 100 nodes.
But not for sure, because you're running faster. It depends on how much faster you're running. If you have ideal scaling, then energy should remain constant, right? You have 10 times more processors, they're running 10% faster, so you use those increased number of processors, but for a lot shorter time. So the energy should ideally remain constant.
But I think most of these nodes are tuned to run for performance, right? So effectively what happens is when the node switches up, the processors are basically clocked up to the maximum order per second. So what was curious was that top graph,
Yes.
where you had between 10 and 100
Yes.
nodes. That was a bit curious.
That's what I'm saying, yeah, that is interesting
That's
result.
an interesting one. I'm not so
Of course,
excited about it.
this is, if I remember correctly, the average of 3 runs, so there is some scatter, but not a great amount
Yeah.
of scatter actually.
So that's a bit interesting one.
Can you say what is the basic cause of the non-linearity of this graph?
Well, basically, if you match it with this plot, so lines here are ideal scaling,
Yes.
meaning if I use n times more processors, my program should run n times faster, right? And you never get ideal scaling, it starts to deviate, right? I use more and more nodes, but actually I'm achieving fewer and fewer extra.
So your program is dominated by communication. It starts to be dominated by
Yes.
communication and
Yes.
waiting, spending a lot
Yes.
of time
Yes.
waiting and burning energy and
Yes.
memory.
Yes, so here you see there are 2 different sizes. One is 8 times bigger than the other, because we thought that maybe, where is it? Yeah, this line with circles, the chunks of the model on every image are becoming too small. So the actual compilation time is just too short, and everything is becoming dominated by communication, which is why we get this deviation. But the larger model really doesn't behave much better. So probably bad program. My fault.
Okay, no more questions. Since time is up, and we shall thank again for the excellent presentation. And as a sign of appreciation, we normally started to give last year books, but the speaker refused the book. He wanted to have a pen with USB, but it was not in stock, so instead we got a battery.
Thank you very much.
60 logo of the PCS.
Thank you very much. So the soap bar. Thank you.